Hi everyone, I'm Sean Bartell and I'm from the University of Illinois. I'm here to talk to you about guided linking, which is a new technique we've developed for optimizing dynamically linked code. So let's start with a motivating example. Let's say you're a developer and you have a function foo that calls a function bar. Bar is a very simple function and we'd like to inline it into foo. LLVM makes that very easy to do. Even if the functions are defined in different files, all you have to do is turn on link time optimization. But let's say one of the functions is defined in a plugin and one is defined in a shared library. All of a sudden, there's no way to optimize this code. There's no option you can turn on or tool you can use that will let you inline a function from one shared library into another. The purpose of guided linking is to fix that and let you optimize code across these boundaries between different dynamically linked libraries and programs and plugins. Guided linking works on existing dynamically linked software without requiring any changes to the code. And by enabling various kinds of optimizations, we can actually speed up the Python interpreter by 9%, or if we optimize together multiple versions of the Boost library, we can reduce the total file size by 57%. But I'll get into the results later. Now I'll give an overview of the ideas behind guided linking. There are basically two problems that prevent us from doing the optimization I just showed. The first problem is that when LLVM optimizes code, it only sees one program, plugin, or shared library at a time. When we're working on a program, the code for any shared libraries it uses isn't available. The solution here is for the developer to compile a set of programs and libraries in bitcode form and apply the guided linking tool to all of them together as one unit. We call this set of software the optimized set. This is sort of like an extension of LTO. Note that if there are any static libraries involved, they'll already have been linked in at this stage. But even if we have all of this code at once, we run into a second problem, which is that the information we have at compile time isn't enough to determine how the code will be dynamically linked at runtime. Any definitions we have in the optimized set could be overridden at runtime by other definitions outside the set, and the exact behavior depends on all sorts of environment variables and configuration files that affect the dynamic linker. We can't safely make any assumptions about which definitions will actually be used. Our solution to this problem is for the developer to provide a list of constraints on the dynamic linking behavior of their code. For instance, they can use a constraint that says this definition of bar will never be overridden by a different definition in a different library. With that constraint, we can safely inline bar into its caller. So the inputs to guided linking are the optimized set, consisting of programs, shared libraries, and plugins in bitcode form, along with a list of constraints on what the dynamic linker will do. The guided linking tool basically does three things. First, we move as much code as possible out of the optimized set and into a new library called the merged library. This will help make use of all the existing optimizations in LLVM, which only work on one module at a time. Depending on the constraints, we might be able to move whole functions entirely into the merged library, or we might have to move just the body of the function and leave a stub definition in the original library that calls the body in the merged library. The original programs and libraries still work just as before, but when you load one of them, the merged library will automatically be loaded as well, and that's where the actual code will be. The next thing we do is to simplify the code in the merged library. If we have a dynamically resolved call from one library to another, we try to replace that with a statically resolved call within the merged library. We want to do this for as many symbols as possible in order to enable optimizations, but we need to check the constraints to make sure it's safe to do this without affecting the behavior of the code. We can also do some other transformations like internalizing definitions in the merged library if the constraints allow it. Finally, we use LLVM's standard LTO passes to optimize the merged library. In effect, these optimizations can now cross the boundaries between different programs, libraries, and plugins, but it's worth pointing out that we can apply any LLVM optimization this way, not just the standard ones. So that's the overview of guided linking. Now I'll give some more detail about the process from the developer's point of view. The first thing the developer has to do is to choose an optimized set. The optimized set can be an arbitrary set of programs, shared libraries, and plugins. The developer just has to compile them in bitcode form. It's okay if some libraries or programs are left out, as long as the constraints account for that. The downside of using a very large optimized set is that you have to optimize and distribute the whole set as a single unit, so if you change a single library in the set, you have to redo the whole optimization process and distribute a whole new merged library. The developer can choose a small or large optimized set depending on the situation. If they want to avoid changing the way their software is distributed, they can apply guided linking to a small set of software that's already distributed as a single unit, like a single software package. But this small optimized set may limit the amount of optimization we can do. An example of a larger optimized set would be an entire Docker container. Docker containers are already distributed as a single unit, and usually no software is added or removed after the container is built. So in this case, it's practical to use an optimized set that contains every program and library in the container. If you want to be really ambitious, you could even imagine applying guided linking to your entire desktop computer. In order for that to work, you would need to have bitcode for every installed piece of software, and every time you install new software, you would have to add it to the optimized set and perform guided linking again. So now that we've talked about the optimized set, let's talk about the developer's choice of constraints. The developer can provide constraints of 4 different types. I'll explain each type momentarily and give you a rough idea of the optimizations it enables, and the more constraints are provided, the better we can optimize the code. Constraints can be applied separately to each symbol used by the code, but in practice the developer will choose some constraints to apply by default to the entire optimized set. Then they can give exceptions to those constraints on a per symbol or per library basis. In this example, we're applying all 4 constraints by default, but we have one exception. We're not applying the no external uses constraint to functions with pi_init in the name. Now I'll explain each of the constraints in turn. The first one I'll talk about is the no override or no external overrides constraint. The example here is similar to the one at the start of the talk. We want to inline bar, which is defined in a library, into its caller, which is defined in a plugin. However, without the no override constraint, that optimization would be unsafe. At runtime, there could be a definition of bar outside the optimized set that overrides the definition we have inside the set. If we inline bar using the definition inside the set, we'll inline the wrong version, possibly breaking the program. By specifying the no override constraint for bar, the developer guarantees that no definitions of bar inside the set will be overridden by definitions outside the set, which means it's safe for us to inline bar. The next constraint I'll explain is the no use or no external uses constraint. We'd like to be able to internalize definitions after we move them to the merged library, in order to enable further optimizations like deleting the definition if nothing uses it. But there are 2 cases where doing this would be unsafe. The first case is when there's code outside the optimized set that uses the definition. In that case, we can't internalize the definition because then the external code wouldn't be able to use it. The second case is when we call DLSim to dynamically look up the definition. Even if we do this from inside the optimized set, DLSim won't be able to find the definition if it's been internalized. By specifying the no use constraint, the developer can guarantee that neither of those cases will happen. Then it's safe for us to internalize the symbol. The third constraint is the no plugin or no use in plugin constraint. To explain this, first I'll provide some background on a detail of how plugins work on Linux. When you load a plugin, by default the dynamic linker uses the rtld local flag, which creates a new symbol resolution scope for the plugin and its dependencies. This new local scope is separate from the global scope, which contains the main program and its dependencies. No code in the global scope will be able to use any symbols defined in the local scope. That creates a problem for us because we want to move code from the plugin to somewhere else. Specifically, we want to move it to the merged library, which might have been loaded in the global scope. When the moved code tries to use a symbol, it might fail if the symbol's definition is in the local scope. It actually is still possible for us to move code like this, but we essentially have to create some dynamic linking tables of our own in order to make sure we look up symbols in the right scope. That can add a lot of overhead, so we want to avoid it. The developer can apply the no plugin constraint to code that will never be loaded as a plugin, or even as a dependency of a plugin. That code will always be at global scope, so we don't have to do any extra work when moving it around. There's actually another option for this constraint. If the developer shrinks the optimized set so it only contains code that belongs to a single plugin, all of our code will be at the same local scope, so again we can move code around without extra work. We can apply the no plugin constraint to the entire set in this case. The last constraint is the no weak constraint, which is short for no weak uses or external definitions. The example for this constraint looks a little different from the others. The optimized set includes 2 programs, and there's also a library which is left out of the optimized set. What we might want to do is to move definitions entirely to the merged library, so that the symbol is exported from the merged library. However, without the constraint, there are 2 cases that make it unsafe to do this. Both cases are caused by the fact that program 2 now sees a definition of bar when it didn't see one before. The first case is when there are weak uses of the symbol. By a weak use, we mean any code that checks whether or not the symbol is defined, either by using a weak declaration or by calling dlsym. By defining a symbol that wasn't defined before, we could change the behavior of the code. The other case where moving this definition is invalid is if there are other definitions of the symbol anywhere outside the optimized set. Depending on what order the libraries are loaded in, the definition in the merged library could override the definition in the other library, breaking the program. The developer specifies the no weak constraint if they know that neither of those cases will happen. With the constraint, it's safe to move the definition. Unfortunately, I don't have time to explain exactly how the merged library is constructed based on the constraints. You can find the full details in the preprint of our guided linking paper. Instead, I'll jump straight to our results. The first program we benchmarked with guided linking is the Python interpreter. For the optimized set, we used the main Python program, libraries, and plugin modules, plus a few extra plugin modules we needed for our benchmarks. We applied all 4 constraints to the code, which implies that we can't use any new plugin modules or programs outside the optimized set. That wouldn't make sense for a typical Python package, but it would be perfectly practical in something like a Docker container where we know exactly which modules will be used with Python. We do need a few exceptions for the constraints in order for the plugin modules to work. For our baseline, we applied LTO with profile guided optimization. The guided linking version also used LTO and PGO on the merged library. In this case, guided linking exposes a lot of new opportunities for inlining, and PGO is important to decide which of those opportunities are actually profitable. In order to benchmark our optimized version of Python, we used the PyPerformance Benchmark Suite, which is designed to track the performance of the Python interpreter. Here are the speedups we get on each of the benchmarks in PyPerformance. On average, we get a 9.2% speedup over the baseline. In the best case, we get a 32% speedup, and in the worst case, we get a 6% slowdown. There are only 4 out of 61 benchmarks that slow down, and we believe these slowdowns are caused by issues with code layout in the merged library. Now I'll show a couple of specific examples that help explain how we get this speedup. In the benchmark where we get the 32% speedup, most of the CPU time is spent in a plugin module called Pickle. This module is processing Python dictionaries, so it has to call the pydictNext function over and over again, which is defined in the main Python library. Guided linking gives us a huge speedup because we can inline this function from the library into the plugin. As a second example, let's look at this code from the main Python library. Whenever a benchmark returns from a Python function, there's some code in Python that reads this global variable, pyFrameType, to find the pointer to the frameDalloc function and then calls that function. Without guided linking, there's no way to optimize this code because you can't tell whether some other library might modify the pyFrameType variable and make this field point to some other function. But guided linking is able to internalize this variable, and LLVM can determine that no code ever modifies it, so it can make the variable constant, and in turn that lets it inline the frameDalloc function into its caller. Now let's look at a different kind of experiment. It's very common to have multiple versions of the Boost library installed at once because you're using different programs that require different versions of the library, and the same thing can happen with Protobuf. That leads to a lot of unnecessary code duplication. In this experiment, we optimized together multiple versions of the same library in order to reduce the size. After using guided linking to make a merged library, we reduced its size with the function deduplicator, which merges identical functions into one without affecting functionality. For this experiment, the optimized set contains several versions of the same library. The only constraint we used was no plugin, which is safe because we don't expect the main program and a plugin to use 2 different versions of the same library. We didn't use any other constraints because we wanted to maintain full compatibility with any programs that might use these libraries. When we applied guided linking to 11 different versions of the Boost libraries, we got a 57% reduction in the total size of the ELF files. On 8 versions of Protobuf, we got a 31% size reduction. For our final experiment, we applied guided linking to Clang and LLVM. We built LLVM with the build shared libs option, creating hundreds of programs and libraries. As a caveat, we should point out that the LLVM code and build system are specifically designed so that you can get better speed and size by compiling everything into one shared library, instead of using the build shared libs option. Guided linking has to be more conservative to make sure it preserves the exact behavior of all these hundreds of libraries, so it doesn't work as well as the option built into LLVM to build a single shared library. But this experiment still indicates what kind of results you might get if you apply guided linking to a project similar to LLVM without an option like that. For constraints, we tested 4 different configurations. That ranges from closed, which assumes that no external code will use the LLVM libraries, to interposable, which imposes no real restrictions. We used LTO and PGO for both our baseline and the guided linking version. In order to benchmark Clang, we used it to compile and link SQLite with the O3 option. Here are our results. For the closed configuration, which uses the most constraints, our optimized version of Clang is 5% faster and 13% smaller than the baseline. Another configuration, open spurious, which allows external programs to use the LLVM libraries, unlike closed, is still 5% faster and 5% smaller than the baseline. On the other hand, both of our 2 least constrained configurations are larger and slower than the baseline, because with so few constraints we need to be very conservative and add extra layers of indirection. Now I'll talk about an idea for future work to extend guided linking. Specifically, I want to talk about a more extreme idea called automatic multicall. You may be familiar with a tool like BusyBox, which is a collection of dozens of different Unix programs combined into a single executable. If we could extend guided linking to create programs like that automatically, we could potentially merge the entire optimized set into a single executable that doesn't use the dynamic linker at all, which could give us even greater improvements, especially for code size. Will Dietz, who graduated from my group last summer, actually implemented a version of automatic multicall, but it only worked in very limited situations. You had to apply it to every dependency of your programs, and you couldn't have any plugins or any symbols with multiple definitions. So a future work idea is to see if we can use ideas from guided linking and lift some of these restrictions. In conclusion, we've shown that guided linking can be used to optimize dynamically linked code as long as you give it an optimized set of software and constraints on the dynamic linker. We've been able to speed up the Python interpreter by 9%. We can combine multiple versions of Boost or Protobuf and shrink them by 31 to 57%, and we can optimize Clang and LLVM to create a version that's both 5% faster and 13% smaller than our baseline. That's the end of my talk, and if you have any questions or if you're interested in guided linking, please feel free to send me an email.